that what we did in the last class. So we start from here. So we realize that this is a parabolic equation. And when this is a parabolic equation, now I think things will be very, very clear to you while we were studying those mathematical basics. That this is a second order in space and first order in time. And then we give a very easy transformation, theta equal to t minus t1, in order to get the equation in terms of theta. And then we enforce these conditions in which one will be initial condition and two will be boundary condition. And that has been written here. And then what we do, we apply the trick, mathematical trick called the separation of variables. My slides are visible to all of you. Can somebody confirm?
Yes, sir.
Great. Now, once we enforce this separation of variables, so in X, I get a, so essentially I assume that this is a linearly independent solution in time and space. And simultaneously, I get two ordinary differential. Essentially, I convert this single partial differential equation into a pair of ordinary differential equations. And these pair of ordinary differential equations have independent solutions, which I collate in order to get the solution for theta. So you can see this is what is you call as capital X is a function of small x, and this is what is capital H is a function of tau. So with a very simple assumption, I am able to really follow the spatio-temporal. Spatio-temporal means space and time. So this is temporal, time. This is spatio, this is space. So I have a spatio-temporal solution for theta. Right? Then what we did, we went for different enforcing boundary conditions. And then what we did, we obtained the constants. And we could see that a general solution comes out something like this. So even with this simpler assumption, the solution is not a very simple solution that is coming out today. And today we will see how gradually, progressively this particular stream progressed, and then we could really come up with different types of analytical and numerical solutions. So, and then we move towards analyzing the lump systems. I mean, you are given, I think, 4 or 5 tutorial problems. This Thursday you have to submit, and there you will find you will need these equations where we say that, say suppose a highly conducting object, if you immerse in a liquid, and then if you cool it down transiently, so you essentially diffuse the heat through the convection process, which is the surrounding fluid. Whereas, the capacitance of this particular object determines that how much it can retain. So in that process, if you just, balance these two, then what happens during the balance of these two, what you get this type of equation, and that can be written as a capacitor, which is in parallel to a resistor. Resistance is coming here because of the convection, and the capacitance is giving you the capacitance that is associated with the internal energy of the system. Somebody yesterday told that this internal energy, Saurav, I believe, right? He told that the internal energy of the system, when you energize the system, basically you are increasing the internal energy. Now, this equation, if you solve, you get a beautiful temperature, a spatio-temporal equation or a temporal equation for temperature. And then if you analyze this parameter HA by rho CV, you essentially get, this is nothing but the multiplication of the reciprocal of the thermal resistance to thermal capacitance. So what is a thermal resistance? For a conductive system, it is 1 by HA. For a conductive system, it is delta X by Ka. Okay, and what is the capacitance? Capacitance is rho CV. Okay. So once you do that, then from there you can get a time constant. What is this time constant? Essentially, the capacitance divided by the resistance. So capacitance will try to hold the heat, whereas a resistance or conductance, reciprocal of resistance or conductance, what it will do, it will try to diffuse the heat. Now a balance between these two will determine the kinetics of the process or the time of the process. Once that is clear, then we went into defining a dimensionless number, defining two dimensionless numbers. One is called Biot number and the other is called the Fourier number. So what is Biot number? Biot number is, say suppose if you have a conducting medium and it is surrounded by a convective medium. So, the internal resistance, conduction resistance to the surface convection resistance, the ratio between these two is called the Biot number. And if it is less than 0.1, then only we can consider the system to be a lump system. Then what we did, we went for a little bit more rather than going for only separation of variables. We solve the problem when you change the boundary condition, right? You can solve the problem in terms of the error function. And we showed that these are more accurate solutions of temperature, right? Say suppose this is T equal to T0 and with respect to, so you may see that here, what is happening? This is X. So temperature is slowly increasing and then, saturating in 1. Right. So in this sort of solutions, what you can get, more accurate solution you can get, when you enforce the error function, and error function has been defined as something like this. These are all different types of mathematical juggleries. You can also assume power series. You can also assume Fourier series. You can also assume them as Bessel functions or like Laplace, this year. What is that called? There is another very important, so different types of analytical, solutions are obtained for these temperature equations. This is one such example. And with error function, you can also do what? You can do like, temporal analysis. So we will do some problems. It is difficult to comprehend just by looking at these solutions, but using these equations, say if this is the equation and this is the boundary condition, this is the solution, and this solution we will be utilizing to compute some of the problems, then you will see that it will look much more straightforward than what it appears right now. Once that happens, then we said that this is a kind of, we talked about, this is a kind of like Neumann boundary condition. Earlier we were enforcing what? We were enforcing all the boundary conditions as what? We were enforcing the boundary conditions as, these are some of the Dirichlet boundary conditions. These are some of the Dirichlet boundary conditions where you define a temperature and an isothermal boundary condition. Whereas, when you define heat flux, you are basically looking for, say, suppose heat flux equal to 0, that means it's an adiabatic system. Okay. So different types of boundary conditions. Say, suppose you have put insulation, right? What is the boundary condition here? You will put a heat flux boundary condition, heat flux to be 0, and that is nothing but a Neumann boundary condition. So we talked about 3 different types of boundary condition: Dirichlet, Neumann, and Robin boundary condition, and we have shown there what is their architecture. So not only the solution, not only the solution of this equation, type of solution of this equation in the form of error function or separation of variable or Fourier transform, but also boundary condition dictates like, how the temperature profile will look like. So first we talked about the convection boundary, heat flux boundary condition. Then also we have talked about the convection boundary condition. Like say, suppose what is being conducted at x equal to 0 is being convected out. This sort of boundary conditions are also in action in terms of heat transfer. And if you put that, you obtain different types of solutions in temperature, and that is plotted here. You may see that that has been plotted here in terms of x. This is you can see this 4 alpha tau. This is nothing but this is alpha is what? Thermal diffusivity. What is the unit? Meter square per second. What is tau? Second. So this is essentially meter square. So meter square to the power half means meter. So x is the distance which is in the x direction, divided by 4 alpha tau is you are dividing by another dimension which is a distance. So x by 4 alpha tau to the power half is a dimensionless parameter. So this is the x directional dimensionless parameter. This is the temperature dimensionless parameter, and these are the dimensionless time. So if you enforce this boundary condition and if you get a solution of this form, so you can plot them like this. Now there are different types of function plotters are there in MATLAB, Mathematica, different software. So if you plot them, you will essentially obtain a solution, essentially obtain a plot like this. And these plots are extensively used for different types of systems. So we have shown certain nomenclatures here like cylinder, sphere, different types of temperature. And then what we did, we went for the plot called the Heisler charts. So what is the utility of this Heisler charts? We will see, like, as we do some problems, we will see that, these Heisler charts are plotted. See why we are doing all these things. say if you look at the heat transfer as a engineering core subject, so essentially the first problem that you face in the industry is that you have, say, suppose shell and tube heat exchanger. So in a shell and tube heat exchanger, you really have to know how exactly heat is being transferred with respect to time and space. Now, we were doing all the calculations, say, for a kind of rectangular Cartesian coordinate system, say, suppose for one dimension, and we saw that those are pretty easy. But moment you get, geometries like cylinder, concentric shells, right? Cylinder with inlets and outlets, the geometry becomes very, very complicated, and there you will find hard getting analytical solutions, right? So what you need to do, you need to really do smart approximations for those geometries and then combine the parameters in such a manner, you come up with this type of plots which are specific to, say, suppose cylinder, say, suppose, rectangular cube, suppose, the geometry that you are doing, it is specific to that. Okay. And then once you prepare the plots, what you do, say, suppose you are manufacturing a car and you need to know what exactly is the rate of heat transfer from the engine of a car. So what you do, you prepare a Heisler chart, which is a representative of that engine, okay, which has a particular geometry, and preserve that Heisler chart for whenever you bring in the geometry, you preserve the chart and make use of that. Okay, and whenever you get these charts, whenever you are doing some calculations, so essentially you don't again solve the equation and then come up with a number, but you preserve the chart, and from there you find out, say, suppose if this is the Fourier number, suppose if this is the Biot number, then what will be the temperature profile? I think Mohit has a question here yesterday, right? Can you please repeat what was the question that you had?
Yes, sir.
You had a question yesterday, which I could not, because of this, network issue. What was the question you had here?
Yes, sir. Actually, the question was about that heat flux, like what is the name of that boundary condition? You said that it's a Neumann boundary condition. So
yes.
Yeah, that's like that was my doubt. Like actually, I didn't know that how it was classified at that time, like how Dirichlet Neumann, and that was, I didn't get that point.
Okay. So just to tell you, clarify the whole point. Say suppose this is a boundary, right? And say suppose here I define the temperature to be T0. So that means I have fixed the temperature here, right?
Yes, sir.
But then say suppose if you have a boundary like this, and then I have put an insulator here, right? So what is the boundary condition that I put here? Can I put a temperature boundary condition here? Most probably no. What I can put a boundary condition here is that dt by dx is equal to 0. Correct? I can say that temperature gradient is 0. Why? Because inside it's a very high temperature, and then I have put a medium which is not conducting at all. So Q is equal to 0, right? That means minus K into dt by dx is equal to 0, applying Fourier law. So K cannot be 0, so dt by dx is 0. If Q has to be 0, dt by dx has to be 0, right? This boundary condition is called the heat flux boundary condition. And this is not, you are not essentially defining a temperature across the boundary. Rather, you are telling the gradient to be 0. So this type of boundary condition is called the Neumann boundary condition. This type of boundary condition is called the Dirichlet boundary condition. A mixture of these two is called all the three, you can see that they are there. Say suppose this is a kind of boundary condition, this is a mixed boundary condition. It's a Robin boundary condition, right? So you have Dirichlet, you have Neumann, and you have a Robin boundary condition, and three different solutions are given to you. All those solutions are a bit complicated. That's why they are always plotted in the graph form for different geometries. Okay, based on the dimensionless numbers. You plot in terms of dimensionless numbers. Why? Because you can see that you have clubbed so many parameters here. You have taken into account the heat transfer coefficient of the medium. You have taken the conductivity, surface to volume ratio, okay, density, capacitance. When you multiply Biot number into Fourier number, you have taken into account all the possible parameters that are responsible for the temperature variation. So is it clear now?
Yes, sir. Got it, sir.
Right. So for a given geometry, Heisler chart talks about what? This is the temperature, right? This is the Fourier number, and this is the Biot number. So what is the Fourier number is responsible for? It talks about diffusive transport rate divided by storage rate. What is the Biot number is talking about? Biot number is talking about internal thermal resistance to the surface resistance. And the game between all the two has been reflected in terms of what? The game between all the two has been reflected in terms of what? In terms of the change of the temperature. So essentially for a particular given point, if you are given a point of a geometry, you will be able to really calculate from this plot what is the temperature at that particular point. Say suppose you are given a cylinder, you want to know at a particular point what is the temperature. So if you go to chart and then plug in all the parameters related to conductivity and all, you will be able to identify the temperature. That is the purpose of making Heisler charts. And then say suppose low Fourier number and plate. So you see the charts they look like this, right? Temperature as a function of center temperature in an infinite plate. So you will find numerous such plots of different types of geometries, related to this. This is for a cylinder. Okay, so these plots are already available. Why? Because these geometries, they frequently appear in the engineering calculations. Rather than using equation, I just go and pick up the plot, which is very much relevant to my engineering problem. And then I just from there, I find out the value. Right. So, that helps me in say, suppose you have iron, suppose you have aluminum, suppose you have, different materials. So you will find different plots for different materials also, which have been used. Great. So, we will do some problems from there, you will be able to really calculate. And this plot is very, very important because, Q by Q0 is nothing but a measure of what? It is a measure of heat loss. And this measure of heat loss is plotted in terms of, you can see that Fourier number and Biot number, and this is also what is, this is what is changing in the Biot number. So you can see that using this heat loss is a very important engineering parameter I told you. So this is for an infinite plane, this is for an infinite cylinder, and this is for a sphere of radius r0. So different types of materials, we can really calculate the heat loss. And that heat loss is associated with the temperature difference, right? And that heat loss is also associated with your thermodynamic processes, which is not available. So free energy calculation also helps. So for a given situation, how much energy you have lost, that you can also calculate using these plots. Okay. Don't get scared by all these things. This you will see, there is a smart way to use these plots, and we'll do that in the tutorials. Great. Now you see that, earlier we went for a 1D. So delta square T by del X square alpha delta. Now, if you go for 2D transient, even then you can make use of this separation of variables. So what I did, I made X, Z, and T all linearly independent, and then went through the same process what I did previously. So what is the equation that I have? I have now 3 ordinary differential equations. I will have now, this is my X, this is my Z. Again, these are partial differential equations, and then I decouple them in order to make sure that, I have a linearly independent solution like this. So even for 2D, you can make use of the separation of variable in the same manner, the way you do it for, say, suppose, this equation you have already solved, right? And this equation also you have already solved. So if you plug in those two and then get back here, you will be able to really get a solution which you have done previously. So with separation of variables, although it is not exactly accurate, but you can still obtain the solutions, right? Great. So, I'll come back to this, shape factor, maybe this shape factor before. But okay, so this slide is remaining. Say this is for a plate. Okay. Now for a plate, these are called the asymptotic analysis. So, you can take a plate, you can take a rectangular cross section, pillar, right? And then, you can have different types of geometry starting from plate to cylinder. And this actually tells you like, how exactly you propose, different types of what? Different types of separation of variables. Okay, so it's just a kind of like, giving you a kind of C theta is a solution for infinite cylinder, Px is a solution for infinite plate, Sx is a solution for semi-infinite plate, and these solutions you can combine in order to get different types of solutions. It's just a kind of statement, you can understand from here that how exactly. So this is a very, very complicated second order in space. It's a two-dimensional second order in space and first order in time. Moment I enforce this sort of separation of variable, what I get two partial differential equations, which are again second order in space and first order in time, but both are 1D equations. And these two 1D equations I have already solved previously. If I have those solutions, and then if I get back here in terms of the linearly independent, in terms of the linear independence, so what happens? I'm able to really get what the solutions that I am looking for the temperature profile. So this actually extends that concept into different types of geometries, right? As theoretical things, whenever you do a problem, it will become more clear. Okay, right. I come back to the shape factor little later. Let me just finish this part first. Now, say suppose you want to solve the problem. Let me just open. So suppose you want to solve this elliptical equation numerically. Okay. So can anybody tell me how exactly you went about the derivatives? Say suppose I want to really evaluate dt by dx, right? How do you evaluate dt by dx? What is the first condition for dt by dx? Whenever I write dt by dx, what is the first assumption that I make? Anybody quickly? What is the first assumption I'm making?
So why is that
Temperature varies with that.
Yes, temperature is a function of x, right?
Means.
Very nice. Number two is, what is the second assumption? Number two.
X is an independent variable here.
That is, t is a dependent variable, but t is continuous in x, right? This is another assumption that I make, right? T is a continuous function, correct? If it is not, then it doesn't happen. Then what I do? Say I say that t at x plus h, right? If I do a Taylor series expansion, how do I get it? Can anybody prompt me? What is the Taylor series expansion? Quickly, bolo, jaldi se. So t at x, then what is the second term? Yes, I'm waiting for you.
So t dash of h into t of x. T dash of
h by 1 factorial into del t by del x, right? Right. Then third term.
Sir, here t dash of x and del t by del x mean the same, no?
Yes. Then what is the third term?
H by 2 factorial.
H square by
2 factorial.
d square t by del x square, right?
And
this is the way I go. I can write also d here because it's only one dimensional. And then what I do, what is the first assumption when I evaluate this dt by dx? What is the first assumption that I do? I do the assumption that, what is the third assumption that I have? That is h tends to 0, right? So limit h tends to 0, right? That I put, correct? then what I can say that tx plus h minus tx divided by h is equal to what? Del t by del x, where I ignore all the higher order terms, correct? These things I put to 0. Why? Because of this, as h is going to 0 and t is continuous, correct? This is the this is the formula of derivative, right? This is the formula of derivative that you get, right? Am I correct?
Yes, sir.
Yes,
Right.
sir.
Right. Now, once you are done with that, then the job is easy. How do you tackle this numerically? So you first put a stencil. It is called a stencil. How exactly you go about? Say, let me just draw it clearly. You just put a stencil. What is a stencil? Say, suppose you have a geometry like this. So this is a plate. And this plate, what you do, you divide into, multiple, control volumes, which are small control volumes. Okay. It's a plate with a boundary. And you identify a point in the middle. And this particular point you call as the point I, J. So what is I? I is an array which is on this side, and J I assume to be the array on that side. So this may be I equal to 0. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6. This can be infinite. Then again, this is J equal to 1, 2, 3, 4, 5, and so on and so forth. So essentially, I cross J is an n by n matrix. Right? Now, what is this point that I can call here? What is this next point? If I look at this particular stencil, I have 4 points. This is my central point, which is ij, and I have 4 points surrounding it. What is this point? Anybody prompts me? This is I plus 1 j. Clear? What is this point?
I minus 1 comma j.
I minus.
What is this point?
I comma j plus 1.
I j.
Fantastic. What is this point?
Oh.
I comma j minus 1.
I j.
Very nice. Right? Now, once this is done, say suppose I want to evaluate dt by dx. So now my challenge comes out. I want to evaluate dt by dx, right, at I and j. How do I go about it? I've done just now, right? How do I write that? Can somebody prompt me?
dx plus x.
So what should I do? What should I write? T I plus 1
I
j minus
ti plus 1.
tij. Very nice. Divided by. So I say that, I have divided them in equal units. So this is delta y. Say this is delta y. Say suppose this is delta y. This is delta y. I have divided them into equal units, and this is my delta x. This is again delta x. This is delta x, right? So all these are equal units, right? So this is essentially delta x, and this is essentially delta y. So what should be the denominator here?
1.
This will be delta x, right?
Delta x. Okay, but isn't delta
H is there? H is there, no?
Okay, yeah. So yeah, like one unit
Right.
is there, but delta x will be there. Yeah.
Correct. Now,
Yes.
what are the other ways I can write the same thing? I can also write T ij, sorry, Tij minus T I minus 1
I
j.
minus 1.
j divided by delta x, right? Correct. So that is called, this particular thing is called the forward difference. Sorry. So this particular thing is called the forward difference. Whereas this particular thing is called the backward difference. And what am I doing? I'm converting this dt by dx, which is a ODE or PD, into what? What is this equation? This is what type of equation is this? This is an algebraic equation, right? So you can see that at this particular point, I can convert the whole thing into Tij. I mean, in terms of the temperature which is in this, right? Similarly, what will be my dt by dy? How can I write, like, say suppose I want to know dt by dy, right, at ij. So if I say that my backward difference, forward difference relation, what will be by my dt by dy ij? Can anybody prompt me? What is that?
Tij plus 1.
Tij plus 1.
Very nice. Minus Tij
Tij divided by del y.
delta y, right? Easy. Right? That's the reason why CFD has become such a buzzword. Now you see that. So this is Ij I have taken, this is taken Mn. So this point is Mn, this is M plus 1, this is M minus 1, this is N plus 1, this is N minus 1. This is delta x, this is delta y. Right? Now you want to know dt by dx, you see M plus 1 minus M divided by delta x. You want to know dt by dx, this is the forward difference, this is the backward difference, this is in the y, this is in the y, right? So they have taken in the form of half just to make sure that they can do the delta t by delta x square. Even the way I have done, you can also the same way. You can do with Ij also. You may need another point there. So you get the point here, right? M plus half means what? Essentially, you are doing the derivative here. Right? This is M plus 1. So the derivative is obtained at M plus half n. And the forward difference is obtained here, backward difference is obtained here, forward difference is obtained here, and backward difference is obtained here. These are the 4 formulas. Correct? And equal is replaced by this almost equal y, because we have assumed a Taylor series expansion, and then we have assumed that delta x tends to 0 and delta y tends to 0. So what is my next challenge? My next challenge is to go for, say, suppose I have an elliptic equation which I have to obtain del square t by del x square plus del square t by del y square equal to 0. This equation I have to solve. So how do I go about it? You see that it is very simple and straightforward. So now when you take the second derivative, what you are doing, you are taking the derivative at m half. So how exactly you go about the second derivative? Let us follow our own methodology. Like, how do I obtain del square t by del x square? Let me do it in a different way than what is given there, right? So suppose you have t x plus h, right? So you have tx, then you have got h del t by del x, right? Then you have got h square what? Del square t by del x square. Correct? Correct.
So
It does. Is that h square by 2? Fantastic. H square by 2 del square t by del x square, right? And then you have got h square by 2 factorial, correct? And then h cube by 3 factorial del cube t by del x to the power 3. Now I put the limit to be h tends to 0 and I want to know what is d squared t by dx square, right? I want to really know what is d squared t by dx square. So what will happen to that? So I will have t x minus x plus h minus tx, right? And then I have what? I have h into del t by del x, right? What is del t by del x? It is t. Say suppose I put x minus h, okay, minus tx. Dt by dx, what should I put? I put dt by dx. Let me not do this way, okay? Let me do the other way around. Let me do the other way around. Okay, so suppose you have tx plus h is equal to tx plus h into del t by del x plus h square by 2 factorial into del square t by del x square, right? And then what I do tx minus h. So this is equal to tx. Then what happens? Minus h into del t by del x plus h square by 2 factorial into del square t by del x square. And then I have the higher order terms, right? And then what I do, I enforce h tends to 0 so that all these higher order terms, I say that I can neglect and they can be 0. Now, if I add these two, then what do I get? These two terms cancels out, right? And from there, what should I get? Say t x plus h minus t plus tx minus h minus 2tx and divided by h square. H square by h square 2 adds to h square is equal to d square t by dx square. Right? So I just did a simple Taylor series expansion of t of x plus h, again t of x minus h, and I have obtained, this is true for what condition? There are two conditions. One is h tends to 0 and second is t has to be continuous. Right? Exactly, you see that same thing it has been done here. In a bit different way. They have done it in a bit different way so that it becomes very easy for you to understand. When I have m and n plus 1, I obtain the derivative at half as tm plus 1 minus tm by delta x. This is true for all the four these intermediate points. And then I get for delta t by del x square, but just by when I go for del square t by del x square, what I have to do? I have to get this m plus 1 minus m minus 1 divided by delta x. I'm doing another derivative, right? Del x of del t by del x. And I'm doing another y. So you get what? Tm plus 1 n plus tm minus 1 n minus 2 tm n divided by delta x square. Same formula that we have obtained using what? Using the Taylor series expansion. So this is the del square t by del y square. This is the del square t by del x square. Now, say suppose if I have a Laplacian equation which is del square t by del x square plus del square t by del y square equal to 0. I can write this equation approximately as, for a particular point, I can write approximately this equation as what? Can somebody prompt me? What should I write here? T I plus 1 j, right? Minus, somebody prompts me, what can I write here? 2 tij, right? Then plus t I minus 1 j, right? I minus 1 j, right? Divided by delta x square, right? Then what I can write? Delta t by del y square. T, this will be what? T. Now this you should tell me what should be the the indices here.
ij plus 1.
J plus 1. Very nice. Then
minus 2ij.
2 tij.
Tij.
and then plus
Tij plus j minus 1.
j minus 1 divided by
Del y
Del
square.
y square.
del y square equal to 0. And typically, so you see that this is what? This is a partial differential equation, right? With the help of Taylor series expansion, with the two assumptions that h tends to 0, okay, and then it is a continuous function. So we are able to really convert this partial differential equation into an ordinary differential equation, right? So now you see that the same has been done here. So del square t by del x square is tm plus 1n, tm minus 1n, 2tmn divided by delta x square plus tmn plus 1, tmn minus 1, 2mn delta y square. Now, if you assume x and y to be same, this is called a structured grid. If you assume this to be a square box, delta x, delta y same, so that goes out. And what you obtain? You obtain from there what? All these things can be added into what? Added into this. So this is an algebraic equation. And in this algebraic equation, say this is a infinite space, a plate. So what you do, you have 1, 2, 3, 4, 4 points. So suppose you say that these points you have 100 degree centigrade boundary condition. This is 500. This is 100, 100. So you have a plate where three sides are 100 degree and one side is 500 degree. So each and every point you need the temperature. Say what is m plus n? N. So this will be what? This will be this particular point. What is the temperature here? What is the temperature at this particular point? 100. What is the second temperature? That is 500. Then you have T1, T2, right? T1, T2, 4. So if you just assign these temperatures at different points, right? If you just assign these temperatures at different points, essentially you have 4 equations means you're looking for 1, 2, 3, 4. Correct. So now at 1, what you are looking at, if I put this particular point to be 1, so what is the stencil that are coming out? So m plus 1 n, m plus 1 n, that is coming from T2, right? Then you have m minus 1 n. That means this is coming from this. This is 100. Then you have m n plus 1, that is 500. So you can straight away see T2 is here, 500 is here, 100 is here, and then you have T3, and then you have minus 4T1. So for 1, you have this equation. For 2, you have in the left hand side that is 1, that is T1. Then at the top you have 500. Then at the right you have 100. Then at the bottom you have got T4, and then for this own thing you have 4T2. For T3, you may see that in the left you have 100. Then you have in the right you have then at the top you have T1. Then at the right you have T4, and at the bottom you have 100 minus 4 T3, because TMN is going 4 TMN here. And then for 4 again you can see that T3 is at the left, T2 is at the top. Then you have 100 in this side and 100 in this side minus 4 T4. So essentially for these 4 points you have these 4 equations with all the boundary conditions satisfied. You know all the numbers here around this. So if you solve these 4 equations, how many variables are there? T1, T2, T3, T4. How many equations are there? 4 equations are there. So if you solve these equations simultaneously, it's an algebraic equation. You obtain T1, T2 to be 250 degrees centigrade and T3, T4 to be 150 degrees centigrade. So you have a numerical solution obtained. This is an elliptic equation. Using the elliptic equation, you have obtained, see, del square t by del x square, del square t by del y square. You have converted to an algebraic set of algebraic equation. Those set of algebraic equation you solve simultaneously in order to get the temperatures at point 1, 2, 3, 4. Is it clear? Or should I repeat? Is it clear to all of you? Any questions here? Any doubt here? Because I am going to shift gear now. Any doubt you have up to this point, whatever we have discussed for last 10 minutes, do you have any doubt here?
Sir?
Yeah.
So basically, if we are given temperature at the boundaries, we can divide them into del x and del y, and then we can use to calculate the temperature at the points.
Yes. As many number of points. So that's what I am telling. So here I have just given 4, right? But 4 is a very less number of points. In numerical, what you do, you divide this particular space into n. In this space, you have n. In that space, in this direction, you have n. In this direction, as many as you put, the solution is more accurate. Clear?
Yes, sir.
So number of, see, you have an elliptic equation, you put a number of in the x direction, you put a number in the y direction, and here how do you solve these equations? Typically, you know, this is, you can say that, you know, coefficient matrix you can separate out t1, t2, t3, t4. You can write this entire thing as what? You can write this entire thing as, you know, very simply you can write this entire thing as, say this is, suppose you have a coefficient matrix, right? Say A1, A2, A3, A4, AN, right? And then, you know, this is A11, A12, A13, okay, A1N, right? And then A21, A22, A23, A22, A23, right? You know, something like that. So and so forth, right? A11, 12, 13, A21, A31, sorry, this will be 31, A41, A51, right? Something like that, right? Now this matrix, and then what you have, then you have this multiplicative factor, that is T1, T2, T3, T4 until Tn. This is equal to, say, suppose 0. Now, if you do a matrix inversion of that, you will be able to get what? You will be able to get the solution for this equation, and that you do using the numerical method. So essentially, when you go for an n by n matrix, you have this coefficient matrix to be A. Okay, right hand side to be C. This is the variable T, right? So T is equal to what? A inverse C. So you take the inverse of A and then you take the C, and then essentially these are done using the iterative method. And with the iterative method, you can get for all T1, T2, T3, T4, you can clearly see that a computer program can be written. And that computer program can be written in order to, so this is the, I have just given you the 2D entire, you know, solution for this 2D conduction, 2D heat transfer, right? Now, in this situation, what we did, we just took del square T by del x square, del square T by del y square to be 0, right? In this situation, you can see that now we have integrated another complication, the time component also. So how do we go about? Space, we discretize the same manner, the way we have discretized the space. And in time, you may see that how exactly we go about this. So for time, what you do, you go like this, that. So you do a time marching. So how do you obtain del T by del T? So you do what? So T, Ij, P plus 1. P plus 1 is your time component, minus T, Ij at P divided by delta T. So you use the same formula for forward difference. You can also same formula for backward difference, right? In order to really make sure that, you know, you are taking care of the time component. So how are we converting? This is, we have already understood. This is, we have already understood. Right hand side, you know, we are writing the derivative in terms of time. Now, you just notice here, I have maintained everything at P. Time equal to P. This is the previous time step. And P plus 1 is the next time step. So all temperatures at the level of previous time step, and then here I am doing a time marching towards the next time step. That's the only change that you need to make, right? And in that process, you convert the entire thing into a algebraic equation and again solve iteratively in order to get the solution. So essentially, now you can really consider any geometry. You can really consider any geometry in the world. This is a cylinder I have given. So you just break it down into pieces. as many number of pieces as possible. And then individually, you develop a stencil for ij. And you know the boundary conditions has to be given. You know what are the boundary conditions that are possible. And from the boundary conditions, you convert your elliptic equation. See, one thing you should remember that all these equations that we are studying, they are true for any geometry. If you remember the way we develop the equations, they are true for any geometry. They are not geometry specific. Equations are phenomena specific. They are coming from the energy balance equation that is true for any geometry. It can be for a car, it can be for an aeroplane, it can be for a ship, it can be for ocean, it can be for sun, it is true for anything and everything that is available. The only difference that you have is in the geometry in terms of the engineering devices. Now, as the geometries are different, the boundary conditions will be different. Now, that's what you need to build in terms of your solutions. So you bring in the geometry, you bring in the boundary conditions, and then solve the equations. Boundary condition and the geometry will decide what will be the temperature distribution that is there inside the space and how does it change with respect to time. Any question you have up to this point?
Yes, sir. Sir, that n cross n matrix whose inverse we are like supposed to find. So that is to be like we don't have to manually calculate, right? Like it would be.
These are all computer programs are available. I mean, you can write, in 2 minutes you can write a computer program. Gauss elimination, Gauss-Seidel. There are so many different types of methods. LU decomposition, right?
Yes, sir. Okay, yeah.
You just write an array. You just, this I think is the first, if you learn computer programming, this is the first program that you learn, right? When you define array matrices and all these things, correct? Am I correct?
Yes, sir.
The matrix inversion problem is the main first problem that you do in your computer programming, right? So if you do that, then you just multiply matrix multiplication, and these are all, computers will do for like in split seconds. Everything is done. You have the temperature profile.
Yes, sir.
Right. Any other question?
One more thing, sir. So, like, what is this value of n? Like, how much? To what extent do we take like this? And we
see,
can
when I started my career, if you take n a million, that was a very big, like collar raising event, right? As I progressed in my career, 10 million became the the collar raising event. Recently, one of my student, he did a simulation with 1 billion n. Right. So as the computer power increases, it is actually limited by the strength of the microprocessor. Okay, the parallel computation, whatever algorithms are there. So today the number which is very attractive is 1 billion. It is 1 billion by 1 billion matrix you are solving.
1 million. Yes. That's
so
a big
yeah, h tends to 0, no? That's the whole target. I mean, more is the number of points, more accurate is your solution, right? Of course, generally people don't simulate beyond, like, if you are accurate within 1%, 2%, you don't waste time in refining them further as a wastage of time. But for certain problems, you really require, that sort of mesh where there are singularities, right? So those problems, you really need to go about 1 billion, 10 billion. That is the typical number nowadays people are exploring. Any other question you have? No, great. Yes. Yeah. What is that? What is
it takes for calculating?
1 billion you are talking about?
Yes, sir.
One simulation maybe 15 days.
Oh.
I mean, of course, not, solving 1 billion mesh, if you don't time march, it will be about like, maximum 1 hour, right? But then what we are doing multiple time steps. So you have to remember that I'm not solving it only once. See here you just, if you look at the, let me just go here. So here you look at, say, this t plus 1, right? Say suppose I'm time t equal to 0. I immediately get the solution, right? Then I want to go for 10 second, 20 second, 1 hour, 2 hour, 3 hour. And in that also I take a time step of, say suppose 1 microsecond. So that, I time march it very, very refinedly, right? So a typical 20-30 second simulation in event, which is happening at very fast. And you want to really know that, 20-30 seconds, say suppose 2 drops are coalescing, right? So it's a very rapid event. And then if you really want to resolve the places where they are coalescing, right? So in those sort of situations, you need really fine measures in order to resolve them. And time marching is the event issue here. I mean, how much refinement you need in terms of time also. It is not only space you are resolving it. Space is billion matrix, right? But each time, say suppose 0 second to 1 millisecond, 1 microsecond, 1 microsecond to 2 microsecond. Each time you are solving this billion mesh. So how much is your time marching? That also decides what is the length. Typically, an event which is of about 20-30 seconds. With 1 billion mesh, we take about 15 days to finish the simulation. But this time is going to reduce. Another 2 years time, I think with the microprocessors coming now, this will be again in a day you can do it with the supercomputers and all. Okay. Any other question you have?
Thank you, sir.
Yes. So let us stop today. So Friday there'll be a tutorial. Okay. And we'll start with the shape factor and then we'll progress to the next lecture. Thank you. Thank you so much.
Okay, sir.